Hey everybody, Dr. A here, and in this video we are going to be providing some background information on three-dimensional vectors using Cartesian notation. Now, if you remember from some of our previous videos, there are two common notations or methods to express a vector. One is scalar notation and the other is Cartesian notation. And we've mentioned in some previous videos that when we're dealing with two-dimensional vectors, using scalar notation is usually more convenient. But when we deal with three-dimensional vectors, that's where Cartesian notation is going to be a bit more convenient and almost necessary for most cases. So let's go ahead and start exploring this. Let's start by saying consider a vector A with x, y, and z components. So we know that this is a three-dimensional vector, okay? So let's practice drawing what that would look like in 3 dimensions. What I normally do to sketch this by hand is I start out with my 3 axes, okay? So I'm gonna draw my origin here, and I'm gonna come off to the right here, and I'm gonna call this the y-axis, okay? Now, I know normally that would seem like it should be the x-axis, but we're going to call this the y-axis, and then we're going to come off at an angle here and call this the x-axis. So what we have here is the xy axis kind of at a 3D orientation. It's not necessarily an isometric or orthographic view, those of you who have had a graphics course, but it's some kind of 3D orientation. So where would the z-axis be? Well, at this point, the z-axis would be coming up from that origin. So this is our x, y, z space, okay? So instead of a plane like we had in 2 dimensions, we have a space here with multiple planes. So let's talk about these planes. This plane right here is going to be the xy plane, all right? So our ordinary xy plane is this 2-dimensional plane down here, all right? We also have the YZ plane. So this plane right here is another 2-dimensional plane. What about a third plane that's showing up here? Well, we have the XZ plane, which is this 3-dimensional face over here, okay? Now, if we want to consider a vector in 3 dimensions, well, we're going to, for simplicity's sake, we're going to take the tail of the vector to be at the origin, and we're going to show it coming up like this, okay? Now, how is this going to look like it makes some kind of sense in 3 dimensions? Well, let's call this vector A and give it a name here. So what we're going to do to show this in 3 dimensions is first, I'm going to show its projection down on the XY plane, okay? So what I'm going to do to help me visualize this is at the head of this vector, I'm going to draw a dotted line down here to a point on the XY plane, okay? Now, what I'm going to be able to show here is I have this kind of projected component that's on the XY plane, okay? And this should really be, you know, a linear segment or a straight line right there. That made it a little bit worse. Okay. Now, what I'm also going to do is show its 2 components that lie parallel to those 2 planar axes. So I'm going to show a component that's parallel to the y-axis and to the x-axis. And the way I'm going to construct that is by drawing parallel lines to each of those axes, okay? So let's take a look at what I have here. This dashed red line here is parallel to the x-axis, and then this dashed red line here is parallel to the y-axis. So what I'm able to kind of sketch is this projected shadow, if you will, of vector A onto the xy plane, okay? Now, what about the z-axis? Well, the z-axis or the z component is going to be projected back here, okay? So this will give us the z component of that vector A. So if I were to sketch the actual components, then what I'm going to have here is the y component of vector A, which I'm going to express that as a y j hat, and then I've got the x component here, which I'm going to express as a x I hat, and then sure enough, I'm going to have the z component coming up here, and that's going to be expressed as a z k hat. All right, so there are my three components, the I, the J, and the K Cartesian components, 3 dimensions, okay? So here's what I would do if I were you at this point. I would maybe pause the video and take out a sheet of paper or wherever you're taking notes at and practice sketching this. Practice your 3-dimensional sketching, okay? Because a big part of this kind of analysis is being able to sketch this freehand, okay? So practice the freehand sketching. Maybe you can take a straight edge out and practice using with a straight edge as well, all right? So that's what I would suggest you doing now. So I'm going to keep going now. How would we express this as a Cartesian vector? Well, we would say vector A is equal to a sub x I plus a sub y j plus a sub z k, okay? So this is the Cartesian vector notation of vector A, all right? Now, what if we want the magnitude of vector A, right? What if we want the magnitude of vector A? So I'm going to say magnitude of A is going to be expressed, you know, with these, they look like absolute value bars around the vector itself. And we're just going to use the Pythagorean theorem to express that magnitude, except we have the 3 components now. So it's going to be shown as ax squared plus ay squared plus az squared, okay? So that is generally what we're looking at in terms of a 3D single Cartesian vector with its magnitude. Now I'm going to scroll on down because in addition to a magnitude of a vector, we are interested in its orientation and direction, okay? So let's talk about what that's going to be for a 3-dimensional vector. Well, the orientation of a 3D Cartesian vector can be expressed in 2 ways, okay? So the first way we can express a 3D vector's orientation is by what's called its coordinate direction angles. And we label those as alpha, beta, and gamma, all right? Or the second way is using its projection angles, which we normally call those theta and phi, okay? So let's talk about what that's going to look like in either case. And remember, you could come across 3D vectors that are expressed either by coordinate direction angles or projection angles, all right? So let's talk about these coordinate direction angles first, all right? Coordinate direction angles are the following. We're going to say these are angles measured from the positive axes to the vector in 3 dimensions. All right, so let's go ahead and practice sketching that 3-dimensional vector one more time, okay? So here's what I'm going to do. Again, how do we sketch a vector in 3D? What's the best practice? Well, we start with our origin, and we come out to the right. We call that the y-axis. And then we go back to the origin. We go kind of at an angle. We call that the x-axis. And then we go up, and we call that the z-axis, okay? And then we're going to draw that vector A again. Let's call it right there. There's vector A. And remember that vector A has 3 components, right? It's got an x, y, and z component, just like we drew earlier. So where are these coordinate direction angles that we're talking about? Well, The first coordinate direction angle, which we said is alpha, is going to be the angle measured from the positive x-axis in 3 dimensions to the vector A right here, okay? So if I were to sketch that here, that is alpha, okay? So again, think of vector A sweeping out in 3 dimensions, okay? And angle alpha is that kind of angle that's sweeping out in 3 dimensions with A, but measured from the positive x-axis, all right? What about beta? Well, similarly, beta is going to be another 3D type of angle, but it's sweeping from the positive y-axis over to vector A. So beta is going to be right here. Okay, there's angle beta, all right? And then the third coordinate direction angle, gamma, is going to be measured from the positive z-axis to vector A, all right? So we have gamma sweeping in this direction, okay? So the key thing to remember with these coordinate direction angles is that they are measured from each of the positive axes. So if you have a more complex system where you're showing the negative x-axis, the negative y-axis, or the negative z-axis, we're measuring these coordinate direction angles from the positive side of those axes to the vector, okay? Now, how do we relate all of these together somehow? Well, it turns out that we can establish the following relationships. We have cosine of alpha equals the x component of the vector divided by the magnitude of that vector, okay? We also are going to have the cosine of that coordinate direction angle beta is equal to the y component of that vector divided by the magnitude of the entire vector. And then, as you're probably guessing, we're going to have cosine of gamma equaling AZ divided by the magnitude of A. All right. And again, you know, if you have a statics textbook handy, or maybe even a physics textbook handy, there might be some additional figures that kind of show a graphical little proof of this. But this is how it's summarized. Now, again, the key, I've said it a few times now, is that these angles, alpha, beta, and gamma, these coordinate direction angles, are always going to be measured from the positive axes to the vector itself. Okay, now we also have a Pythagorean identity here that relates all of these together that we're going to end up using from time to time. And that Pythagorean identity is going to be summarized as the following. It turns out that if you say cosine squared of alpha plus cosine squared of beta plus, erase that little dot, plus cosine squared of gamma, that is going to equal 1. Okay, so we have this little Pythagorean identity that relates all three of these coordinate direction angles together. Again, it's the sum of the squares of the cosines of each of these angles equal 1. All right, so that's what we're dealing with when we talk about coordinate direction angles. But we also said that the orientation of a 3D Cartesian vector can also be expressed by its projection angles, which we call theta and phi. So what do I mean by that? What do I mean by projection angles, theta and phi? Well, let's sketch that out. So I'm going to scroll down here. We're going to say, okay, let's look at some projection angles now. So again, we're going to use this as an opportunity to practice sketching our 3D vectors. So let's put an origin here. Excuse me. We have, that's not the x-axis. What is that? That's the y-axis coming off to the right. We've got the x-axis kind of coming down here. And then we've got the z-axis coming up here. Okay, so again, we're practicing our sketching. And then we've got vector A here. All right, so think back to the original figure. We said, and I even used that term before, projection. So what we can do is we can project the head of that vector A down to the XY plane, okay? Now, when we do that, that vector is gonna, cast, the term I use is cast a shadow. It's gonna cast a shadow of itself on the XY plane, okay? Now, if we give that one a name, we can call this A vector prime, okay? Prime, not for derivative, don't get excited, no calculus yet, but that's just gonna be, like I said, the shadow of vector A. All right, let me draw that a little bit better. I have trouble drawing straight lines sometimes. This iPad, there we go. Okay, so when we cast that shadow on the XY plane, and we can, again, we're giving it a name now, A vector prime, we can still break that into respective X and Y components, just like we did at the beginning of this video. So how did we do that? Well, we drew a line here that was parallel to the x-axis, and we drew a line here parallel to the y-axis, okay? And then, of course, we've got this, z component over here. So when we talk about projection angles, typically what that deals with is these angles that are related to this projected shadow of A, okay? So for example, let's use a different color. This could be angle theta, and then we have another angle phi that's going to be in between A and A prime. That'll be phi right here, okay? So what does that mean for us? Well, let's write this over here. We're going to say theta is the projected angle in the XY plane, okay? And that's going to be between vector A prime and either the X or Y axis, okay? So angle theta could be this angle over here between A prime and the Y axis, okay? What about phi? Well, phi is another projected angle, and this is going to be between vector A and A prime, okay? So you see that we have this phi angle that's in between A and A prime, okay? Now, here are some cool things about how these are all related. First thing I'm gonna want to point out is that we have a couple of right triangles that we can end up utilizing to help us perform some of our analyses. Well, one right triangle is going to be, or one right angle is going to be the angle right here, okay? So it turns out that this is a right angle. So this little triangle right here that's formed by A and the shadow of A, which I'm calling A prime, and this projected line, that's a right triangle. And so phi is going to be one of those interior angles, okay? It's going to be an interior angle of this right triangle. And then theta is going to be one of the interior angles inside of this projected right triangle. So as you can imagine, this is a right triangle, and this is also a right triangle, all right? So because these are all right triangles, what can we do? We can use 2D right triangle trig to relate A A prime, theta, and phi. Okay? That's what we can do here. Now, what I would suggest is if it's easier for you to maybe break this down into two-dimensional views, what we can do is do that. We can say 2D views to help us visualize this, okay? So, for example, we could have a 2D view of the XY axis right here. So, when I'm looking down at the XY axis, what do I see? Well, I'm going to see that shadow A prime. Now, where is that angle phi here? Well, if I'm looking down on the XY axis, I've got these two red projected lines. These are right angles. And, not phi, I'm sorry, theta. Theta is right here, right? So this theta is the angle between the positive x-axis and A prime, and it's showing up right here, okay? So again, you can break a 3D figure down into multiple 2D figures to help yourself visualize things. So where would regular A be in this 2D figure? Well, it's coming out of the screen at you, right? It's hovering kind of at an angle phi above A prime, okay? So that's how we can help ourselves visualize this. And please remember, this takes practice. You need to resketch this, redraw it, practice it over and over again. This is not something that you can just watch a video on once and get it perfectly, okay? So let's continue on. What about when we want to learn about the direction of A? So I'm going to scroll up, okay? The direction of A is expressed by the unit vector of A, which is given by this handy little equation. So U sub A, that's a vector, is going to be equal to vector A divided by its magnitude. So a unit vector is a dimensionless vector with a magnitude of 1. And so, again, you might have learned this in a physics course. This video is more for the sake of statics, but you might have learned a little bit about this in a physics course. So if we know that if we're defining a unit vector as a vector A divided by its own magnitude, we can write this as AXI plus AYJ plus AZK all divided by that magnitude, okay? So all I did was I kind of expanded vector A out into its three components, into its three Cartesian components, all right? Now, I can take this, a step further. I can take this a step further and say this is going to be equal to AX over magnitude of A times I plus AY over mag A times J plus AZ over mag A times K. Now, all I did there was I took this denominator and I said, hey, this is a common denominator of these three terms, and then I put it underneath each of those three terms. Now, think back to earlier in the video, what are the definitions of AX over mag A, AY over mag A, and AZ over mag A? What are those? Well, those go back to how we defined our coordinate direction angles. So guess what? We can rewrite the unit vector of A as cosine alpha I plus cosine beta J plus cosine gamma K, because of those definitions of those coordinate direction angles. So that's a handy little relationship to utilize. Now, what we can also do is we can rearrange this relationship, and really any version of this relationship, and solve for vector A directly. So, of course, you can reimagine this as A vector equals magnitude of A times the unit vector of A, okay? Now, you might be wondering, why am I kind of, repackaging this and going in circles? Well, when we get to some example videos of, numerical examples exercising these concepts, you could be faced with problems, that make you go in any direction utilizing these relationships. So that's why I'm kind of emphasizing how we can, reimagine and re-envision these relationships, okay? So now let's get to the, really good stuff. What happens when we have several Cartesian vectors acting concurrently? Well, just like we saw in 2 dimensions, if we have several 3D Cartesian vectors acting concurrently, all we do is we add, or, in some problems you might want to subtract, but we combine their corresponding components. So for example, for multiple 3D force vectors, what we can say is a resultant vector is going to be equal to the sum of all of the vectors acting in the system, okay, force vectors acting in the system, and we can say that's the sum of the x components times I plus the sum of the y components times j plus the sum of the z components times k. And again, in the case of statics and physics as well, but definitely statics, we're dealing with force manipulations, right? We're dealing with looking into finding resultant forces, okay? And so if we want that resultant Cartesian force vector, we just follow the same process like we saw in 2 dimensions and some other videos. And then, of course, if you want the magnitude of a resultant force, that's just the Pythagorean theorem, but with these 3 components. So it would be sum of the forces in the x direction squared plus sum of the forces in the y direction squared plus sum of the forces in the z direction squared, and make sure that that square root is over all of that. So that's our background information on 3D Cartesian vectors. Hopefully you found this helpful. If you did, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.